Now, there are other ways that you can do this, of course. That is, there are other ways you can create a training set that is randomly selected, a certain proportion of them, and a test set that is the same. We're going to use the party package that has the C tree, which I believe originally stood for classification tree or condition tree, which is appropriate for, we have to load up the party package appropriate for a classification task. And note, when you load up party, you get all these other packages that party requires. And it's always a good idea before you use a function to query it with the help screen. So we'll do that. We say $C tree. It's a conditional inference tree, but it works with both continuous and nominal. So it's not just for classification. It works for numbers. It works for censored data like survival analysis, ordered data like nominal ordered data or just nominal, and multivariate response. So it handles any sort of classification or prediction task. But there are some foibles of the C tree function. For example, it's very sensitive to missing data. It fails. So if you have missing data, you've got to deal with that. Okay, but so anyway, let's use C tree. Okay, now C tree, as we see here, uses a formula. The formula is the model, where you say, and what we're trying to do is we're trying to predict species as a function of everything else. And there are only 4 other variables. So instead of writing that formula again and again, we just say we store the formula in an object. There's the formula, and we just assign the whole formula to this object. And then we can call the function, we just call the object that contains the formula, and you have to tell it the data, which is on the training data, and it'll put the output in this object, iris_C tree. So we do that, and we can look at what was actually output, and you'll see it's just a list of the rules, the partitioning rules, or the breaks in the tree. And it's easier to interpret these visually, so that's why we don't belabor this point, but you can see the output by highlighting the assigned object. What we're going to do is let's look at we want to know the prediction. Okay, so it's been trained, but let's make a table out of the predicted values. And the predicted values from the training data should be pretty good. So we're going to make a table out of them. And sometimes this table is called a confusion matrix, because what it shows you is, in the rows, it shows you the prediction of the tree as far as the target variable class. For example, this first row tells us that the tree, now mind you, it was running on the training data, predicted 40 would be Setosa species, and it was right 100% of the time. It also predicted that 40 would be versicolor. And actually only 37 were versicolor. 3, it was wrong on 3. 3 were virginica. And then it predicted that 32 would be virginica, and it was right on all of them except 1. So the error, if you want to call it error rate or misclassification rate, actually is pretty low. And we'll come back to that, but let's take a look at the tree. Let's actually print the tree. And all this does when you say print actually just shows you the rules again. It doesn't really do anything. Printing just sends it to the printer. It's easier to interpret by plotting the tree. So if we say plot, which is a method, plot to a generic function, we get something that we can more readily interpret. What the tree does, first of all, a tree is just a basic building block. And most tree functions, and I think C tree is among them, most of the tree building functions look at every single predictive variable, not a limited subset of them, looks at every single predictive variable and chooses to make its first branch or split based on the variable that results in the most division on either side, the most purity on either side in the categories of the resulting branches or leaves. So these are leaves, that is, these are where the predictions are made. So it looked at three of the variables. We had four of them in there, but it said these three have the most clout, and petal length really is the most significant in terms of differentiating the outcome into species. And when the petal length is less than 1.9 centimeters, they're always setosa, 40 of them, always. And when petal length is greater than 1.9 centimeters, they can be either virginica or versicolor, but they're not setosa. So that's a very pure split. These resulting on this side are different than these. Okay, and then then it considers all of the variables remaining after it makes this first branch. Considers all the variables remaining, which one has the most clout in cleanly separating on one path or the other the types, the classes in the leaf. And when petal width, after you've already made this first branch, and you know petal length is greater than 1.9 centimeters, then when petal width is less than 1.7 centimeters, they're almost always versicolor. And if it's greater, they're almost always virginica. And it's pure. The diversity is minimized. They're not diverse. They're very different, the two groups that result from that. And then finally, petal length is, when petal length is less than 4.4, they're all versicolor. When it's greater than 4.4, you get some versicolor, but some virginica. So that's how you interpret that, and it corresponds exactly with the confusion matrix. If you go back up to the confusion matrix, you can see these numbers in the leaves. We have 40, N is 40, setosa. And here we have, these are probabilities, 1.8, 0.6, 0.4. We have 21 versicolor here, and we have 19 something here, but actually 3 of them are virginica and 16 of them are versicolor. So we have 21 versicolor and 16 or 37. And then we have 3 that were misclassified, these. Then down here, we're right every time but once. So that's the way that works. You can also note we're calling plot's generic, calling it there and here, but we're specifying the type of tree, and we're saying simple. All this does is draws a different variant of the same plot, same graph, but it uses Y to represent the proportions in each of the 3 classes. This one they're all setosa, so it's 1, 0, 0. There aren't any that are virginica or versicolor. And then this one was 0, 1, 0, but the numbers are represented in the N, with N equal to 21 and N equal to 19. And somebody pointed this out in the Tuesday class. These numbers do mean something. These numbers that you see, these are branches, leaf. I mean, these are the square gray areas are leaves, which means you actually have a classification result. Do correspond to the numbers that you see up here in the rules. 1. There's 1. Every time you see a leaf, it has an asterisk. There's 2, that's a leaf. then you have 1 here again where you go down here. You don't get your next leaf until you're down here to 5 here. So the numbers do actually correspond to the rules. Okay, but so that's the training. But predicting, testing is different, and that's really the acid test, is when you apply the tree to predict membership in a new observation that you haven't trained on. And so that's what predict does. Predict takes the output object and we use it, we apply it to the test data, and we assign the output to this test pred, and then we're going to tabulate the predictions. And we get another confusion matrix, but this is on the 45 that were held out. And it does pretty well on the new data. Perfect on Setosa, 10 out of 10, 12 out of 14 on Versicolor, and then perfect on Virginica, 14 out of 14. So it does pretty well. Okay, but C-tree, which we looked at the help for the function, can handle both classification and regression numerics as the target variable, but also ordinal, also ordered, arranged ordinal, ordered ordinal, does have some problems. Missing values are a problem. And when you use, if a variable is not considered, if the variable doesn't, if it's in the training set but it doesn't appear in the decision tree, then even though it's not in the decision tree, like in this case, pedal, let's take a look. In this case, sepal width. Sepal width does not turn up in this decision tree. But it's still, you must still have this variable sepal width in the test data set because it was trained on it. So you can't just leave it out even though it has no direct bearing to the branches, to the choices made in the tree.